What's going on, everybody? Name's Nick. I have a PhD in theoretical mathematics, and I'm going to talk about machine learning with stochastic gradient descent algorithms and finding the most optimum curve. Actually, I'm just joking. I don't have a PhD, but this is kind of a good theme with TensorFlow. TensorFlow.js is that we're bringing ML to a larger audience here, and JavaScript we think is a great opportunity for this. So with that, let's get started. So traditional thinking for machine learning is most people assume that it happens in Python, right? There's a lot of data science that happens thanks to NumPy. But is that really the case? Is that really the best case? So I wanted to show this graph. Has anyone seen this before? This is the TensorFlow Playground. This is a resource we have online. It was built by some of my colleagues on the East Coast. And what this does is a visual that kind of shows how data flows through a neural network. And there's different activation functions. And you can kind of get a good sense as to what a very simple neural network is doing. So when we built this project, we had a lot of fun doing it. And we were thinking, you know, we might be onto something here. There might be a lot more opportunities for doing machine learning directly in the browser. There's a lot of opportunities. The first thing is you don't need any drivers or anything to install. If anyone's installed the CUDA framework for Linux, it's kind of complicated. It takes a while to get set up. In the browser, there's nothing. You just you run your JavaScript code. The browser tends itself to a lot of interactions with frameworks like D3 and so on. So there's opportunity to sort of bring ML into this space. And also the browser has a lot of great APIs for interacting with the camera, sensors, other things we can use for training data and inference. And the other great win we get with doing ML directly in the browser is the data stays directly in the client, right? There's no XHR to server. There's no user credentials or security we have to think about. We can actually do that directly on the device. So stepping back to the TensorFlow Playground, this project itself was like 400 lines of JavaScript code. It wasn't a lot. Some of it was some WebGL shader scripts we wrote. And we had an idea of what we can kind of get going. So about a year ago, we launched this project called DeepLearn.js. It's an entire open source project, and it brought linear algebra, which is the backbone to machine learning frameworks, to the browser. We took that project and aligned it with core resources we have here at Google for TensorFlow and launched TensorFlow.js. So this is a framework we launched back in April now. Wow, long summer. And so we've launched this at April, and we have a browser and a server-side runtime. And since we launched it, we've had a lot of great community. This is one of the first projects we worked on. It's called the Teachable Machine. You can train using your web camera. This is a green label, this is a purple label, this is an orange. It sort of gives a good intro into the basics of machine learning with some image recognition. This one's a great community one that was built recently, and it's a self-driving car, and it's actually done entirely in the browser. So these are all examples we have. We have a link at the end you can check out. But this is a pretty cool one. This is an animated GIF, obviously. But someone built this game that just recently, and the little box thing moving at the bottom is the game. Like you're trying to avoid getting hit by the balls, but the model itself is learning to avoid the balls all using our framework. And finally, this is one of the cool ones. Magenta is a project at Google, a research project for doing machine learning with music. How can you automate and generate music? There's a few great examples. This one's a digital synthesizer that learns how to play music. And again, it's all stuff you can run directly in your browser. This one's a new API that just came out. External community developer built a Face API.js. And you don't really have to have anything. You can give it a photo, and it'll find facial features. So this is actually my son. This is Frank. And you see 99% sure that's his face, and it sort of found his eyebrows and everything. Okay, so what do you get with TensorFlow.js? So there's two main components to the framework. We have a Layers API, which is a Keras-like API. If anyone's done anything with Keras, the model syntax is very similar. But below it is the core API. That's the meat of the machine learning library. And it's not just for deep learning. You can do data science with it. We have about 120 ops that ship in that core package. And in the browser today, we power that with WebGL. So we utilize the graphics card or graphics resources through the browser to do accelerated linear algebra all through WebGL. And server-side, we also ship a node bindings that allow you to run that same model code that you would do browser-side with optimized low-to-the-metal C code that we ship for core TensorFlow. And it gives you access to like optimized AVX instructions with CPU, GPU with CUDA, and we're working on cloud integration with the TPU, the Tensor Processing Unit. Yeah, Keras model. Those who have worked with TensorFlow and have done any saved modeling, the Python side, that'll be the similar API. Okay, so there's a lot of stuff you can do with TensorFlow.js out of the box today. First one, you can actually just write a model from scratch directly in the browser. This works pretty well. The browser itself has a limited resource set, so getting started, it's an awesome platform, but you will run out of resources eventually. One of the really cool stuff, we have a bunch of demos for this to show off, but pre-training models for inference. So this is a model that was trained somewhere else. Could be a cloud-based model, wherever. It came from Python or Keras, and we have some tooling to take these artifacts and serialize them for the web, and you can load them directly in the browser, or even on Node.js. And then retraining. So this is transfer learning. This is taking a model and then actually just training the top bits to skew towards our data set. Okay, so let's walk through a little bit of API. This is, sorry for the math, but this is machine learning, so you kind of get into it. This is this is a plot of data we have here, and it sort of curves. And this is a classic fitting case of finding the direct fit to this polynomial. So the function is f of x equals ax squared plus bx plus c. So we're going to actually take this code and implement what it would look like in TensorFlow.js. So first case is to import. So this is ES6 style import. Sorry for no Babel or compiling or webpacking here, but just straight code. So the first thing we will do is import our package, which is tf.js, and we'll namespace that as tf. The next step is to declare 3 variables. These are the variables we'll use in our model, our very simple model. tf.tensor, TensorFlow, so tensor represents a data structure. And then we're going to mark them as variables, meaning that through the training, we can actually change the values under the hood. And the 0.1 is just the initial value that we'll assign those variables. Okay, so a lot of code here, but this is our f of x function here. This is how we would call add and multiply, square root, multiply, so on. We have some sugar with chainable APIs for JavaScript that make this a little cleaner, so that's much easier to read. So we're going to use the output of that function, f, into our model in the next slide. Okay, the next step here to do is declare a loss function. This is what we will feed into our model to tell it how far off it is from that curve. And we're going to be using that good stochastic gradient descent algorithm, which is usually called SGD. That's what that is. So this is just an optimizer that our library provides for free to take the difference in our loss and train it so that our model learns how to fit to that curve, which we're going to do in this for loop here. So epochs, those who aren't familiar with the term epoch, that is an epoch is a pass through your training data. So if you have 1,000 things, it could be 1,000 iterations. It just depends on the data set we're training on. For this, I think there's like, I don't know, 200 plots. So you can think about 200 for loops. And through each one of those, we're minimizing the loss. XS is the data. That would be the actual inputs on the graph. And YS is the label. And so as this model trains, it learns how to do stuff. OK. This one's a little bit more of a complicated example here. This is a recurrent neural network. This is more of a, using our higher level layers API. To give you an example, oops. We're going to solve this particular problem. Like, if anyone looked at this, they would say that's just 100, right? 90 plus 10. But we're going to break this into inputs where it's 9, 0, the plus sign, 1, and 0. So we're going to pass that into an encoder LSTM. LSTM is long-term, short-term memory. And this is all sugar we provide on the model, and so you don't have to know all these details. So our model breaks this into 3 components and then writes it out into the decoder LSTM, which knows how to go 100. OK, walking through this same import step here. And the next declaration here is declaring our model. So tf.sequential, this is in our layers API. This is declaring what we call a sequential model. A sequential model is Keras style, where we just stack layers. So this is some chunk of a model. This is the next step, and so on. So we initialize with that top part, the encoder, as an LSTM with our particular inputs and repeat vectors. All these are very technical terms, but it's essentially the top part for the encoder. And then, again, as it's sequential, we're just sticking 3 more chunks in there to find our output, which the money line is TF layers activation of softmax, which forces our data set to our particular output. The next step is also very Keras-y. It's model.compile. That takes our layers we've done and generates the model behind the scenes and makes sure all of our inputs are validated. We're using a different optimizer. This isn't our friend SGD. This is the Atom optimizer. This is all like for future reading if you get into it. But and then we want to know how accurate our model is, and that's the metric stuff. On our website, we have all these intricate API parts all documented, so feel free to look there. Last line is model.fit, which is actually saying, take my training data XS and fit it to train on the LSTM, which outputs that 100. One key JS thing here is the await. Those who aren't super familiar with this is the nice async callbacks. Instead of chaining promises, we're just going to wait on a promise to return here. Model.fit actually just returns a JS promise. OK, importing existing models. So that was pretty like diving deep into the LSTM world, and this one's much more fun. So we have this model we built. It's an image classification model. And we actually worked with a team here in the San Francisco office for this demo. It's called the emoji scavenger hunt. So there's 200 different emoji icons that we've trained in the cloud to recognize like with a webcam on a phone. So for this one, I actually have a little video I'm going to show. It'll make much more sense.
This is an umbrella. So is this. This is a slice of pizza. So is this. Emojis have become a language of their own. We use them every day to communicate in our text and emails. So much so that it's easy to forget about the real-world objects they're based on. Which got us thinking, could we create a game that challenges people to find the real-world versions of the emojis we use every day? Introducing Emoji Scavenger Hunt. Emoji Scavenger Hunt uses TensorFlow.js. Open source meets machine learning meets JavaScript meets fun. It works like this. We show you an emoji. Use your phone's camera to find it before the clock runs out.
Hey, you found pen.
Find it in time, and you advance the next emoji. While you're searching, you'll hear our machine learning system doing its thing.
Do I see a toilet tissue? Was that a tub? Is that a glove? Hey, you found watch.
See if you can find all the emojis before the timer runs out.
Do I spy a broom?
Emoji Scavenger Hunt, powered by machine learning. Start your search at g.co/emoji scavenger hunt.
Do I see a URL?
Cool. So that gives you a kind of idea of what the fun stuff you can use with ML, right? We didn't have to talk through LSTM encoder and decoder layers. We're taking a pre-trained model and importing it into an app, and we've built this whole application. This is all live. All these demos you can actually run on our site. This one works great on a phone as well. You can feel free to try it out. There's 200 classifications. It'll repeat like what it thinks it's seeing, which sometimes it's kind of funny. All right. So I want to walk through what actually happened in that demo from a TensorFlow.js perspective. So the image classification model we used in that demo is called MobileNet. It's a very common lightweight image recognition model. And internally, it's got like an object detector. It can help detect particular objects. And when you train this model, you say, this is a stapler, this is a watch, this is a banana, and so on. So all that has been trained in the cloud somewhere. We actually trained that with a colleague in Tokyo, and he provided us the saved model artifact from Python TensorFlow. So we took that and we imported it into our scavenger hunt application. And the steps that went into this was just saving the model, so the model's been trained, and training a model involves shifting the weights, finding where everything is, and serializing that to disk. Very high level, but this is what the API on the Python world looks like. We've built a session and a graph, and everything gets trained. And once we get done, we actually call builder.save. And the save model graph for TensorFlow is actually very dense. There's lots of different components inside the graph. There's nodes for finding training graphs for obviously shifting the weights, and there's even like inputs for data pipelines. The data pipeline stuff in TensorFlow actually is very low to the metal. So we have a tool that goes through and finds just the bits we need for doing inference or predictions on our model, and then just pulling that parts out and then serializing it for the web, which is JSON and binary bits in 4 megabyte chunks. Those who have used Keras, this is the Keras API, the sequential model, and so on. And they use an HDF5 format, which is a little bit different. It all comes in one big JSON file when we convert. And then we hit the conversion step. That's where we take that inference graph out, serialize the weights, and provide you with the inputs you need to load it into TensorFlow.js. So this is done with a Python tool. You can pip install it and then run it. This one, the saved model has a little bit more inputs. We need to find the output node through that inference graph. So the reshape one is actually the very end of MobileNet. And we have some output paths where we're serializing it on our disk. And the Keras one looks very similar, a little less inputs because the sequential model, we know where the output is. And then the final step is loading it. So this is the JavaScript specific parts. Here we've declared a model. I think it's legible here. So const model, we use what we call a frozen model. A frozen model is when we're converting it, we're actually freezing all the weights so they can't change. So that's why we call it a frozen model. It takes 2 inputs. One is the model URL, which is the JSON file that has the declaration of all the ops in the inference graph, and then the weight URL where we store all those weights in serialized bits. The weights will always be the larger chunk. The graph itself is very lightweight because it's a small JSON blob, but the weights can be quite large depending on which type of model you are using. Then we pass it to the feed. This is the input. This is the entrance to the MobileNet. And then we can do predictions directly on that model. Again, for comparison's sake, this is the Keras specific one. We're going to load just one file, which is a large JSON file. That has the weights embedded in it, so it can be large to load. And then we can just run predictions. So walking back through what we actually did. So the key takeaways for graph optimization with the TensorFlow converter is, like I said, we pull out that inference graph, and we actually optimize the graph itself. So there's a few ops that can be condensed and optimized. So you're not actually running through every op. There's some that we can chain together. Again, weights are optimized for the browser. So 4 megabyte chunks are great. They cache really nicely in the browser. So you only have to hit that load once if it's a larger model. Those who are going back to the page will have the weights cached and ready to go. And currently, this converter tool supports about 120 plus of the most commonly used TensorFlow ops. A lot of them are image recognition. We're working a lot on audio and text models right now, so the op parity continues to grow. And we also support the common TF Keras layers, as we highlighted earlier. Okay, this one's actually a pretty cool demo. This is another model that we're importing directly in the browser. It's something we just came out with not too long ago, and it's a model called PoseNet. And PoseNet itself is an off-the-shelf model that's been pre-trained, and it can find human figures, so like eyes, nose, and then skeletal key points like my shoulders and stuff. So let me slide over here, and we will. So I've just this is our web browser cam here, and it's using my laptop here. The component on the right's a lot of different things you can play with, but this is the out-of-the-box PoseNet model. Previously, so you can see as I move my arms or whatever, it can detect. It's sort of creepy having the blue dots on your face, but there's a bunch of interesting demos people have built with this, because off the shelf you get a model that can do key skeletal points and do things. We have a demo called Move Mirror, where you like do dances and it finds pictures that have people doing similar poses. So, anyways, this is all fun stuff. You can download it. Actually, you don't have to download anything. You can go to our website and try that out. Okay, training in the browser. So this is the next step. We've just highlighted two models where we actually did no training in the browser. This is all trained somewhere else, and we brought it and ran inference directly in the browser. The browser itself also allows us to do some training. So this is usually what we call transfer learning. Is probably the best case, we think, for the browser with just that limited resource set. We did want to, actually, I wanted to show one more demo that shows this off. Okay, so this is a fun game we built, another game. There we go. Okay, this is Pac-Man, and obviously I think everybody here probably knows Pac-Man or the gist of Pac-Man, but traditionally, like there's a joystick you use, or like the keypad up, down, left, and right. What we're doing is we're going to do transfer learning on this model so I can play with my face, which is kind of a fun usability thing. On the right here, I've got 4 boxes, and what I'm going to do is collect, as I'm holding down my mouse, I'm moving and collecting about 75 pictures there, and right, and then left, and down. So as you can see, I'm moving around because I'm getting a wide variety of angles for the image to learn. And then if I click the train model button here, all in the browser, that's the ML model training that top level to be more specific to my face. So once I click the play button here, okay, you can see the joystick light up where if it's thinking what I'm doing here. Okay, this is harder to do. Okay. There you go. They gotta move my face. Yeah. That's a hard angle to do that on. Normally we have like 2 people do that and someone trains it while we're talking through. But anyways, this is all a demo you can do, again, from our website. It gives you an example. On all the code is open source. So if you want to take this example and apply it to another application. But again, all we did was just do a little bit of training really quickly in the browser, and it'll let us build this demo. All right. So we've kind of shown off a bunch of demos, and I wanted to sort of step back and talk about performance and where we sit. So all the image classifications we've done, except for PoseNet, have all used this MobileNet. That's a specific version. I'm sure it's old by now. But MobileNet is a good benchmark because it's not a huge model. It's something we can run in the browser and on mobile browsers. They get pretty decent frame rates for continuous inference off of the video camera. So these 2 graphs are actually Python benchmarks. So this is running MobileNet on the command line Python TensorFlow. There's 2 benchmarks. The bottom one is actually on like a 13-inch MacBook Pro, and that's the AVX. So this is CPU build. There's no graphic acceleration on this. And the top one is a really expensive desktop that we have at our office for doing these things with a GTX 1080, which is a currently, NVIDIA is top of the line for like maybe another week or two. So it's super fast. It's like a little less than 3 milliseconds per inference time. So that's every image can get predicted in a little under 3 milliseconds. And it's about a little under 60 milliseconds on the CPU. So where does, this is Python. Let's see where the browser kind of stacks up. It's sort of in between. Running that like super beefy GTX 1080, we're pretty close to the Python CUDA. And this is all browser-based. So the laptop itself is tricky because the MacBook we're using actually has an integrated graphics card. So it doesn't have that separate chunk of memory to do all its graphic stuff. It actually shares a lot of the resources with the host CPU. So we have a lot of ways to go. We're sort of working a lot on this right now, heads down work for improving areas for browser performance. I'll talk about that a little bit at the end of this talk. So that sort of rolls into what we could do browser side. Where does the server side stuff come into this? There's a lot of interesting things we think we can do with JavaScript. There's a lot of opportunities in this space. One of them is the ecosystem. I'm sure this group is probably pretty familiar with Node.js, right? There's a ton of NPM packages. You can assemble a lot of stuff and get great applications without having to build everything from scratch. And there's awesome deployment strategies with GCP and Azure, Amazon. You know, there's a ton of different ways of hosting. So we think bringing ML into this ecosystem here is going to be pretty cool. A lot of stuff you can do. One of the other great advantages to doing machine learning, data pipelines, accelerated math, and Node.js is V8 is super fast. It's about 10 times faster than the Python interpreter. So there's a lot of opportunity for making really fast, nice, clean ML fronts. One of the other great things, too, with the server-side stuff is you get access to hardware. So in that previous slide, we saw like, oh, well, we're doing everything through WebGL in the browser. Server-side, we can use very low-to-the-metal optimized C code for CPUs, AVX 512 instruction sets. A lot of work on that front coming. And then GPUs with CUDA, so very high-end CUDA will. And then Google's own TPU, which is the Tensor Processing Unit. It's like this custom-built card for our data centers to do as much parallelized math as we can. OK, I wanted to show you how easy it is to actually use the node bindings that we ship for server-side TensorFlow.js. So this chunk of code here is, those who've used Express know what this method's doing. It's really simple. Express is this framework in Node.js for doing like a HTTP server where we can have really easy endpoints. So there's an endpoint for /model. And in /model, there's a request and a response in the callback. In the request, we're going to send it some data to a theoretical model to do predictions. And then we're just going to write the prediction out. So very simple model, prediction and response. So this actually works out of the box without installing our node bindings, but you will actually get no parallelized mathematics. You actually need to do this one line of code, which is just the node bindings. So once you import this, it actually brings in the high-end C code to do optimization. So once we run this script again, we're now running with just the full power TensorFlow under the hood, just one line of code. OK, what can you do server-side? All those models that we've used, the conversion tool, work directly with the node bindings. There's no mismatch parity with the server-side or the browser-side stuff. Everything works right out of the box. Today, we're shipping a variety of builds, Mac, Linux, Windows, CPU. So that's AVX instructions. So that's a little bit of optimization. And we also have GPU for Linux, and I just finished Windows today. So next week, we'll have Windows GPU with CUDA. And then full library support. So all of the layers in the core API all work with our node bindings. OK, so one more demo here. So this demo kind of highlights how you can leverage Node.js, the ecosystem, and everything to do a model you probably haven't seen before. So Is anybody familiar with American baseball? Baseball like that's going on down the street? Okay, there's one, okay. So, all right, a little visual. In baseball, there's a player called the pitcher, and the pitcher throws a variety of different types of pitch, right? There's like a fastball, which is a high velocity, usually not much movement on the pitch. And then there's a curveball, which is a slower pitch, but has much more movement, change-ups. All this data is available from Major League Baseball Advanced Media. They have a data set called PitchFX, and it's a free open library, and it's just full of sensor data. So I think, like I said, there's a game going on down the street. So every time a pitcher throws a ball, these sensors in these stadiums pick up the release point and give you all sorts of inputs. There's where the ball kind of came out at an X, Y, and Z, a three-dimensional coordinate, and then the velocity at those coordinates, the speed, and so on. So what we did was we took that raw data and built a training set and built our own model. So we can actually predict right when the ball is released what type of pitch it is. So it's a pitch classification. Don't get too hung up on baseball if you don't know it. We're just trying to solve like a classic machine learning problem of taking raw sensor data, feeding it to a deep learning network, and making a classification. Okay, so one more demo here. All right, let's clear it. On my left-hand side of the screen, this is just a web browser, and it's using Express Framework. And we are using the Socket.io library for doing client-side to server-side communication. On the right, I have a terminal that I'm going to start a node server. And this node server is actually just going to start training from scratch that baseball data, and it will report out on the left. OK, so again, my command is like node, and then I have a server.js. So I start up. This is all Mac CPU, low-to-the-level Mac code. And on the right, my console's estimating every epoch so that past that data set where my accuracy is. The blue graphs are, so it reports all the data through Socket.io from the client to the server. And we're drawing the 7 different types of pitches our model knows how to understand, how accurate it is. So it's not very good at fastball, two-seam, and the slider. So those are different types of pitches. But every time it goes through the data, you can see the bars are moving a little bit more to the right. One of the cool things with Node.js is we have the ability to just easily fetch in another chunk of data. So we have this live button here, and this will load recent pitches that the model has never seen before, and those are reported orange. So the blue was our training data. That's how good we are with our training, and the orange is with newer data that this model has never seen before, how accurate it is. So the curveball is an easy one to predict because it has a lot of movement. And then you can see it's 95, 96% accurate. So as this server continues to run, it's just getting more and more accurate. I think it says like 88, low 90%. But anyways, this just gives you an example of how easy it is. You can take pre-built node packages and have a full suite with not a ton of code. All of this is on our GitHub page. I have links at the end. So we'll dive back into that. So let me kill that before my laptop melts. OK. Yeah, here's a good illustration of that demo. MLB Advanced Media has a large XML file set. We've parsed it all in our node server, and we're feeding it into our model, and then we're reporting all that training to the on-device experience, which was my laptop. So you can see the full circle. OK, performance. Let's talk a little bit more about performance. So I showed you where the browser benchmarks were. Like the integrated graphics card, a little slow. But let's see where the server-side performance stacks up. So this is that same benchmark, the Python benchmarks of like 2.82 milliseconds and a little under 60. So we just kind of launched this in May, actually. And we're getting started, and we're still trying to find more optimizations. But we're happy to say the node bindings are just as fast as the Python, if not a little faster in a couple spots. So pretty exciting stuff. You can run highly optimized TensorFlow code that's just as fast as Python today through our node bindings and using our TensorFlow.js APIs. OK, so what are we doing next? What's the team working on? We just launched a bunch of stuff this past spring and over the summer. And we have a few new things we're working on. One of them is a visualization library. One of the hard parts with machine learning in general isn't so much you constructing your deep neural network. It's curating all this data and finding the edge cases and making sure your model doesn't overfit or undertrain or have anomalies that throw off your classification. So I have a colleague who's working on this library. I think we'll be open sourcing it within the next month or two, but it's a full visualization library to help visualize what your machine learning library is doing, or your neural network's doing, what you have in your data. So we're just getting started on this visualization front. We're going to continue to push this. Another great API we're coming out with is our data package. Those who've used TensorFlow Python, we have a tf.data package that does really high-end data streams. We're actually bringing that to JS side. So on the server side front, that's low-level C code for doing parallelized data operations. And then also in the browser, it's easy hookups to feeds like the web camera and other sensors. So you don't have to say, how do I take my image and convert it to a tensor and pass it in? We actually just feed that data directly off the webcam into a model. So that's coming up pretty soon, sometime this fall. In the browser, so I sort of highlighted those performance benchmarks. I don't want to scare you off too much. That the integrated graphics card does really good for everything. All the demos you saw were running live. We're actually projecting here and doing like real-time inference. So it's pretty quick. But we are working on a lot on this front. WebGL is a great getting started benchmark for what we can do with linear algebra in the browser. WebGL has some shortcomings. There's everything is rendered as a texture behind the scene off camera. There's like you would do a 3D library. And there are some performance bottlenecks from going and grabbing those textures and reading the data back and bringing it into the host. So we're looking at some new standards, working directly with some of the Chrome groups, web groups for web GPU, and so on. We're also looking at things with compute shaders and other more advanced GL topics for improving performance there. A lot of the focus we've been doing, and you'll see in Ping's next demo, audio and text is a big thing we're kind of focusing on. We've showed a bunch of image classification models. Now we're kind of shifting and looking at what we need to do to bring in audio and text. And I mentioned Web GPU, which is a standard that's sort of out and proposed, very early stages, and then compute shaders. OK, Node.js support. So this is some interesting stuff we're starting to look at. We want to have a better integrated cloud solution. So we're looking at things, serverless training in the cloud, where you can just deploy a model and only pay per instance for inference time. We'd like to have like a very easy to use accelerated TPU experience where you could deploy your application and then run that serverless. We're actually working on importing all of the core TensorFlow ops on the node bindings. So everything you would be able to find in Python, you'll soon be able to find in our node package. Yeah, so libuv is a nice underpinning for Node.js for doing async. So we're working a lot with libuv to make a nice thing where you plug in your model and you're not worried about blocking your application's thread. So we're starting to look at async support internally with libuv. OK, sorry, I've thrown a lot at you. Ping's demo is pretty awesome. It's a little bit more focused. We're just kind of showing you the whole ecosystem of everything we're doing in the JS front. Showcase the core API that was the fitting the polynomial, kind of a little bit more meat and potatoes of your ML front. The layers API, sort of showcase that with the 90+10. There's a lot of our demos on our site are all built on the layers API, so we recommend you use that. The save model and carriage model exporting, that was our Pac-Man demo, the PoseNet, and the what was the first one we did? A lot of demos. Anyways, there's a few that we have, and then our Node.js bindings. The emoji scavenger hunt. That's right. How could I forget the emoji scavenger hunt? It's because I didn't get to play it today. That was the thing. OK, so we want to thank you guys for your time. A lot of our stuff's on the js.tensorflow.org site. And this is our root of our GitHub. Everything we do is open source. We don't actually have any internal contributions. So everything you can find off of is off of the TFGS GitHub page. We also have a community mailing list. Feel free to take a picture of that. I'm not sure if you can write that down. But all those are linked out on our main js.tensorflow.org. We have a gallery repo off of that main TFGS. It isn't just the stuff we've built, but things that the community has built. There's a bunch of blog posts, tutorials, really awesome support on YouTube, all community driven too. And then we have models repo. This is another new thing we've been doing where we ship some of these pre-built models over NPM, and you get a wrapper API, so you don't actually have to worry about taking data, putting it into tensors, and getting output. You just say model.predict, and it'll give you some output. So there's a few things we have in our models repo. I think there's 2 or 3 models right now. All right.